So, welcome back again to the course. So, we have seen that what is the optimization flow in the last class. So, now we will see what are the constants are there which you can put, that means while you are working with DC environment. So, at that time what are the comments. So, we will take a quick look on that, that means what are the comments available and which comments is related to what purpose, that means you will use for what purpose, that we will see. So, now you can see that constant related comments, that means by which you can put the constant. So, they are like set underscore minimum library, set underscore operating condition, set well load model, set well load minimum block size, then set well load selection group, set clock uncertainty, set clock transition, set drive strength, set load, set port fan out number, set resistance. So, all these are that means constant related comments. Okay. So, it is not that the list is only this much. So, list is very bigger. So, there are several comments which you can put in a DC environment to put different type of constant. So, then there are reporting comments which are available, that means which are mostly used. I have just highlighted only the mostly used comments for reporting purpose. They are like report annotated delay, report area, report attribute, report bus, report cache, report shell, report clock, report cluster. So, there are list of report, that means report related comments by which if you type these comments, so at that time the DC will give you the corresponding reports. So, then reporting comments, again it is continued. Okay. So, I am not going into the details of this. So, here by actually each of this name with this extension, it shows that for what purpose you will use this comment, like report underscore FSM. So, if you are using a FSM, so what are the FSM, that means the information about the FSM that you will give, the DC will give you the about information about the FSM. So, report hierarchy will give you the hierarchical design aspects of the report. So, if you want, then you can also save it by there is a comment. So, report underscore hierarchy, then the report where it will be saved, that means by the name where it will save, there you have to specify the path along with the corresponding extension, that OK.rpd is the report extension. So, please, or .log is the report extension. So, please save in this location with this extension, you have to put the name. So, then optimizing with multiple library. So, multiple library means what I said, that there are in multiple library, whenever you are working with a library. So, at that time the libraries provide three type of library, one is best case, one is worst case, and another one is typical case. Okay. Specify those. So, in the first you say the set link library worst case .db, then target library is the link library, and then minimum library is worst case and minimum version is best case, then operating condition is maximum of worst case or minimum is best case, and the source is like minmax.cons, this is configuration file, and then fix hold time fix violation. If you want to fix, so automatically it will try to fix those hold violation. So, then you can compile, and report timing, here it will see, that means if you just write this comment on the command prompt, you will see the results on the command prompt itself after typing this comment. So, if you want to save it for that means for your future reference, so you, by name you can save it. So, suppose I want to preserve the cells, references and design whenever we are saving it. So, at that time or working on it. So, at that time I said that you have to use don't touch network. Okay. So, if you use this command set don't touch, so whatever instances or whatever design you will mention, that will not be touched. Okay. So, that is why actually here get nets. Okay. Here these are the command like get nets, my nets, then set enable keep signal dt.net true, and then set don't touch this net. Okay. So, this is one command prompt, and we will see this how it works whenever we will work on DC. So optimizing the data paths. So how you can, that means optimize the data paths, it by actually shares the data path operators, then extract the data paths, then explore better solution that might involve a different resource sharing configuration, allows the tool to make better trade-offs between resource sharing and the data paths. Okay, so all these are like used for optimization of data paths. Okay, so then creating the path groups. Okay, so how you can create the group path, like if you use this group path command, this allows you to control the optimization of your design, optimize near critical path and optimize all path also. Okay, so the that means command is group underscore path minus name group 3 from input 3 to via this ff1/d with the weight of 2.5. So this is the, that means syntax for putting that comment. So optimizing near critical paths means, so a design compiler calculates the maximum delay violation of for each path within the critical range as something like this. That means we have already seen this example earlier. That means if the clock period is 20 and if I said that okay, maximum delay is 10 for these 3 inputs ABC and the critical range is 3, so at that time it will show the violator, host violator as a, so as it is getting only that maximum delay. So then controlling the automatic path group creation. So to create the path group before optimization, run the set auto path group command after reading the RTL. So analyzing and elaborating and reading the SDC constant file. So actually all these design constants, so why we are focusing whenever we are talking about design compiler, so at that time why we are more bothered or why we are more focused on the constant file here, because whatever constant file you will use a design vision or design compiler to synthesis your netlist file, that design constant file will be used everywhere in your corresponding that means full path. That means whether that will be used in timing analysis, that will be used in physical design, that will be used in any other case for formal verification, for any other rest of the, that means after synthesis whatever process is there, this design constant will be common everywhere, because you cannot change the constant there. That means here the synthesis you have done with different constant, and the that means physical implementation you have done with different constant. That is not it is feasible, you can do, but that is not a that means valid solution for that, because the constant that will not change, the constant will remain from top to bottom, that means that will remain same. So that's why we are more bothered about constant file here in this early stage of design. So here you see that create underscore auto underscore path groups minus mode, it is RTL group. That means we will create the path groups to RTL mode, then compile ultra. If you want to remove, then remove auto path groups, it will remove the auto path groups. Then report QOR means report the quality of results, how it, that means what is the quality of the results you are getting after doing this. So then you can change that the upper path create auto path groups in the mode of RTL. So you also can that means after mapping also you can also create the path groups like minus mode mapped. Okay, so then you can run you can change there. In the previous example we have seen that okay, compile underscore ultra, there is no mode is that means in which mode I want to compile my design, that is that I have not mentioned. So if I want to change it to incremental compile mode, so at that time I have to mention minus incremental. So then again you have to you can remove the path groups, and then again you can check the quality of results. So and then how you can isolate the input and output ports. Okay, so and the input ports are isolated in the following case. That means when it is isolated, when they drive one or more input pins of a cell having several input pins, and when they drive one or more input pins belonging to different cells having several input pins. The output pins are isolated in the following case to ensure that the cell driving and output port does not always drive some internal logic within the design, or to specify particular driver cell at the output ports. Okay, so how you can do that? So you can say that okay, set isolate underscore ports all outputs minus driver is IVD API. So the same thing is that okay, here all outputs you have in that means set, so all inputs also you can isolate. Okay, that means there it will be like all minus inputs. So this is the inserting, that means this is that means how you can insert the logic on output ports. This is one of the example, and then like one example is there. So you see that here one example is there, that means this net is basically, this feed through net is basically connected to the first AND gate and the second AND gate. Okay, so this is basically dependent, that means that is basically going through that. That means that means same net is connected, once it is connected to design B, and then it is connected to the another, that means design A. So this is a feed through path. So now how to that means fix these heavily loaded nets. Okay, so what you can do, you can write this set driving underscore cell minus leave cell for, that means that is to IO, then balance buffer from this IO pin, and then again load 1 to load 2. So whenever actually you do this, that means you run this command, that set driving cell then balance buffer, so automatically this feed through cell will, as this net is already heavily loaded, so that's why this path will be branched to a different for going to the second AND gate input. So that will be done while it is needed, and you have to mention it manually. So how you can optimize the multi-bit registers? Okay, so single bit registers, multi-bit registers means suppose there is a bus bit for the registers. So how you can optimize those? Replacing the single bit cells with multiple cells reduces the power, clock tree power, and the number of clock tree buffers, the area due to shared transistors, and optimized transistor level layout, and the total clock tree net length also it has been, that means reduced for multi-bit register if you that means optimize the multi-bit registers. So the following script shows a typical RTL bus in interference flow for multiple registers. So what is that flow? So first thing is that manually you assign the bits to specific multi-bit registers, that is create underscore multi-bits minus name, then name is my underscore multi underscore edge 1 with this edge underscore xy star. Then you have to choose this timing driven multi-bit register mapping. So how can you set? Okay, that you can say that set multi-bit options minus mode timing driven. That means here I am doing that manually. That timing driven mode will be followed for multi-bit register mapping. So then you just run this command compile design minus scan with gated clock. So clock gating will be inserted, and then insert DFT scan logic, then compile in the incremental mode with this scan chain inserted. So after that this placement based register banking flow is that that means in the previous example what we have seen that using this scan insertion we are creating the multi-bit, and then again we are running this compile ultra in the incremental mode, then we are trying to find out, or then we are trying to optimize the multi-bit registers. So here this placement based register banking flow says that here you have to select that set app underscore where with this physically aware that means constant, here we have to put. So this is another aspects of design compiler which you can do for optimizing the registers bank, and this is actually placement based or floor plan based, here you can do. So then this is another example of the again optimizing the multi-bit register optimization. Okay, so then optimization for multiple clocks per registers. Okay, so that means if each of the registers is basically connected with or the registers are connected with multiple clocks, so at that time how you can optimize those, that means paths. So to restrict the propagation of clocks so that exactly one reaches the registers, you can use either of the following commands, that is set underscore case underscore analysis or set underscore disable underscore timing. Okay, so to allow multiple clocks to propagate to a register, you have to ensure that this timing enable underscore multiple underscore clocks per reg variable is set to true. Okay, so that means you have to set, okay, this timing underscore this particular command is true. So then it will check for whether there is multiple clocks which is arriving at the registers, that is that means fine or not. Okay, to check that. So then define multiple clocks at a pin or port by using minus add option with the create clock command. Okay, so that means once create clock has been create one clock. So create clock with the period, then the waveform, then the clock name. So here if you want to add another source like clock 1, clock 2, clock 3, clock 4, something like that, so at that time create clock minus add you have to put. Okay, so this minus add option to specify multiple generated clocks on the same source or same pin. So ideally the one generated clock must be specified for each clock that fans into the master pin. And then this master clock option to specify which clock is the master clock. That means though it is suppose with the that means clock it is connected, and from that clock we are creating multiple clocks by copying it. So at that time we have to specify what is the master clock or what is the system clock. So then this source option, minus source option is to use for specifying the clock source, which is the clock where from the clock is generated, that is the pins or ports where the clock waveform is applied to the design. Additionally, when you use this minus add option along with the create clock and or create generated clock commands, you must use minus name option so that clocks that are defined on the same pins or ports have unique name. Okay, so that means from the master clock, if you are generating other clock, so at that time you have to define the name on, that means by differently you have to name for each of the clocks. Okay, so here is one of the example for that. So here you see we are having like 4 clocks, clock A, clock B, clock C, clock D. So in the first flip flop, clock A and clock B has been applied with a multiplexer, and in flip flop 2, clock C and clock D is applied with one multiplexer. Okay, so how you can say that? Okay, so here you have to set what is the false path. Okay, and then here you see create underscore clock minus clock name A with the period of this, and get ports is the clock. Create clock B with period of 8 and minus add, because we are adding the clock and the get ports is clock. Then again for C and D, again we have to create like in the same way. Okay, and here one thing is that we have to calculate the whether there is any false path available for flip flop 1 to flip flop 2. Okay, so that's why here you see that there is the path has been calculated from clock A to clock D or clock B to clock C, right? So then this latency of that clock that has been set using these commands, set clock latency. Input delay has been set with this command, set input underscore delay. Then false path from clock A to clock B and clock B to clock A is also find out. So then high level optimization and data path optimization, how you can do high level optimization, you can do this this tree delay minimization and arithmetic specification. So what is tree delay of minimization? We will take one example in the next slide, and then we will see. This resource sharing is common sub-expression elimination algorithm. So common sub-expression means suppose there are several expressions. So among them one of the expression is common. So we will take that thing out and it will be reused in the further following further, that means expression for implementing those functions. Okay. So here you take one example here. For the first thing is that this Z1 A B has been added with C, and this Z2 is B and D added with C. Okay. So here you see that we are basically we need four adders, okay, for doing these things. So Z1 is one of the expression, Z2 is another expression. So here what we are doing, we are taking the commons, that means we are sharing the sub expression. So what is the sub expression? The sub expression is B plus C. So B plus C is basically common in both Z1 and Z2. So that's why B plus C is common and taken out as this B plus C here in the right hand side, and then that has been added with A1 for implementing Z1 and added with D for implementing the Z2. So that means here the requirement for this adders are 3. So that's why that means from 4 adders now I can save 1 adder. Now it becomes the same expression can be implemented, this Z1 and Z2 both can be implemented with a smaller number of adder, so that the area is also smaller and the circuit is like this. Then again another example is there, that means 2 adder then 1 multiplexer. Okay. So instead of doing that, what we are doing, so we are putting that means the multiplexer in the up, then we are basically adding. So here we are in the first case we are using 2 adder 1 multiplexer, in the second case we are using 2 multiplexer and 1 adder. So that means we can save 1 adder with the cost of multiplexer, as adder cost is much more that means higher than the multiplexer cost. So that's why we can save the area also, save the area here in this particular architecture. So then data path optimization. Data path extension can be done. Suppose I have to add this 5 number A, B, C, D, E. Okay. So how I can do that? First A plus B, then C, then D, then okay. E is the output. Sorry, E is the output. So A plus B first, then C, then D, and E is the output. And each of the, that means adder is carry propagated adder. So instead of that means doing that, if we use that carry save adder, so at that time that will be done in a different way, like A and B first, then C and D at the second. Okay. So using carry save adder we have done, we can do it in parallel, and then we can that means add it using this. So this is a serial operation. So here you see that area is 24,924, but here for this if you use carry save adder for doing the same thing, so at that time the area requirement becomes 15,870. Okay. So this is serial operation. Now timing wise, if I want to implement it, so at that time instead of doing this in a chain, that means A plus B, then it has been added with C, then it has been added with D, instead of doing that, what you can do, A plus B, and here in this side C and D, then A plus B results will be added with C plus D results. So at that time this 3 level will be collapsed and it will become 2 levels. So by that though the number of, that means adder will remain same, so we can improve the timing. So this is data path optimization. So advanced data path transformation, how you can do advanced data path transformation? So advanced data path transformation can be done from sum of products to the products of sum. Okay. So that means now if one expression is there, that is A star B plus, sorry, A star C plus B star C, so that will be transformed into A plus B star C. So that means here sum of the products is changed to products of the sum. that means A plus B. If D is there, then C plus D, something like this. So then comparator sharing, so that means if there is multiple comparison, that means things is happening, so at that time we can optimize this using this parallel constant multiplier or operand reordering. We can achieve this sharing of the comparator, and we can achieve a advanced version of the, that means or optimized version of the data paths. So the tool can rearrange the operands of multipliers or comparators to produce different quality of results. Explore trade-off between the common sub-expression elimination sharing and mutually exclusive operations sharing. Design compiler can undo the CSC sharing in the GTEC netlist and generated by HDL compiler to facilitate the optimization combination of CSC and this mutually exclusive operation sharing. Okay, both between these both of the sharing, that means design vision can take the, that means decision that okay, using this particular that means sharing I am getting more better results, so or we are meeting the specification, so okay, I'll go with this. So we can at that time it can use either common expression sharing or it can use mutually exclusive sharing. So for today's lecture, this is it. So we will continue our lectures on design compiler basics on the next lecture. Thank you.